Hey guys, this is an example video where I'm going to show you 3 different ways to compute a definite integral. So let's just get right into it. I'm going to be computing 2x plus 1, so this integral from 1 to 4, 3 different ways. So first using area formulas, then Riemann sums, and then using the evaluation theorem. So this is just kind of a way of representing the same thing. So just as a note, you can't do all 3 methods for just any integral. I have made a strategic choice. If you want to understand that more, I'll explain this at the end of the video. And what is the point of this? So the whole reason I'm doing this is to show you that definite integrals are way more than just antiderivatives. If you walk away from integrals and you say, oh, it's just computing antiderivatives and that's it, then you don't understand what integrals stand for. Like this is kind of an important point in calculus. So this is why we're kind of doing this, to drive this point home. Okay. So starting with area formulas, so here's kind of the idea behind this. You might be given this definite integral and told to compute this without using antiderivatives. So your brain should kind of default to then that hopefully you can use an area formula to figure this out. And I went ahead and graphed this line, 2x plus 1, so that's always going to be the first thing that you want to do. And then you want to just notice, so your limits of integration from 1 to 4. So here's 1, here's 4. So basically then, this doesn't always work, but usually when you're talking about definite integrals in area, we try to strategically give you an integral that will be above the x-axis, because then you will get the area here. So this is all above the x-axis, so we're good to go. And so as you investigate kind of this shape, you'll notice you can kind of break this up into pieces. And this is a really common thing that you have to do with this, and then you just use known area formulas. So for instance, I have a triangle right here and a rectangle right here, so then I just use my area formulas. So this is, let's see, 3 times 3, so this has 9 units squared as the area. And then this is a triangle, so I take 1/2, the base is 3, and then let's see, the height is 1, 2, 3, 4, 5, 6 tall. I go up 6, yeah, 6. So then this will ultimately just give me also, also 9. So the area in this case, then I just add those 2 areas up to get 18 units squared. And so that would be the value of this definite integral. So another way to think about definite integrals is that it captures area above the x-axis. The next way is doing the good old Riemann sum. So we have a theorem that says that these integrals are actually the limits of these crazy Riemann sums. And so I've just kind of written out the general formula here. And this is for a right Riemann sum. It doesn't matter if you decide to do this on the right or on the left. It's totally up to you. And so this a and this b, that actually corresponds with your limits of integration. So in this case, I am going to compute this from 1 to 4. So this will be my a, this will be my b. And then my f of x, my function, is this 2x plus 1. So my f of x is this 2x plus 1. So one thing that's important is that you are able to take the integral and then kind of transcribe it, I guess, into this language, if that makes sense. So I'm not going to take the limit for right now. I'm just going to work on the sum. So to begin, so just to save myself room, I am just going to work on this whole crazy part, which is already a lot, right? So let's get into this then. So first I want to change this sum to be specific for the limits of integration. So the way that this is going to look then, this is going to be 1 plus k times 4 minus 1 divided by n, and then 4 minus 1 over n. So the only things you can fill in here are the a and the b to start, okay? So now what you want to do is you really want to sort this algebra out. So if you are trying to practice your Riemann sums, like these are a big algebraic slog. So what I would recommend, just work on the inside of this function here. So just simplify this part as much as you can. Maybe pause the video here and then hit play when you're ready. So I am going to go ahead and work this out. So this is going to be 1 plus k times 3 over n. This part over here is 3 over m. So I'm going to just continue to work this out. So this is going to be, so this is goes from k equals 1 to n. So this is going to be 1 plus 3k over n, and then all of this times 3 over m. Okay, So now what I need to do is I really need to plug, I need to work this out. So basically I need to plug, just to be nice and clear, this part here, this is f of this part, I need to plug that in to my x's from up here, okay? So that's kind of the next part of this, is we want to plug this part in, and we might have to kind of mess around with how this looks. So you kind of work through this, and then you, as you keep going through the problem, you have to start making decisions whether or not how you want to simplify things. So maybe you want to pause the video here and then start to kind of work this part out and then hit play when you're ready. So I am going to go ahead and work through this. So this will be 2 times 1 plus 3k over n, all of that plus 1. So let me just put these square brackets around here for right now, and then this is going to be 3 over m. Okay, so at this point, what I want to do is I really want to focus on what matters in this problem. So remember, my index here is the k. So this 3 over n, this isn't really doing anything for this particular sum, so I can factor it out. So let me clear some space for myself. And now let me just take this 3 over n. I'm just going to bring it out in front of this sum because, again, it's not really doing anything. And at this moment, it's kind of just extra noise that's kind of confusing. So the 3 over n's out in front. Now what I want to do is I also want to focus on this piece in here. What can I actually do? Well, I can distribute the 2 at least. So let's do that. So let's see, I'm going to keep the square bracket here. I'm going to distribute the 2. So this becomes 2 plus 6k over n. And then I've still got this plus 1 at the end. Okay, so now I can go another step farther. So let's see, this will be 3 plus 6k over n. And now we've got to think about what we know about Riemann sums. So let me show you a couple of helpful things. So these are algebraic rules for sums, and you can pause the video if you need to write any of these down. I've actually covered these in depth in other videos, so I'm not going to go through them again, but I figured that this might be helpful to kind of point some of this stuff out. So we already used the constant multiple rule, bringing the constant out in front. So what I need from this, I need this constant value rule, which is right here. And then the other thing that I'm going to need one of these sums here. Let's see if I can get it pull up. Okay, so you've got summing the first n terms, n squares, or n cubes. So again, pause the video if you need to write these down. These are kind of the key things that we need to work through this problem. So this is a lot of work, right? So what I'm going to do is I'm actually going to split this up now into 2 separate sums. And then remember, my whole sum is actually just around this k. So what I would recommend is maybe you try to finish this off, simplify this as far as you possibly can, and then hit play. But if you're trying to follow along with me, at least split it up and then figure out what of those rules you can use, and then hit play when you're ready. All right, so I'm going to have this 3 over n, and I'm going to put the square brackets out here now as I split up my sum. So this is k equals 1 to, so I've got this sum, and then I've got this sum. And now what I want to do as I look at this is say, well, this 6 over n, this is all being multiplied by k, but this sum is really around the k. So I want to get rid of as much noise as possible, because what I'm really trying to do is I'm trying to make it look like this so that I can use this particular formula here, okay? So I'm going to go ahead and just factor out, so it's 3 over n, and then I've got all this stuff here. So I haven't done this, and so I'm just going to bring out the 6 over n so that now I can bust out some of those formulas. And so now I can start actually evaluating these sums. So I need to clear some space again. And from here, once again, this is a really great stopping point just to see if you can evaluate from here. Otherwise, let's see. So if I work this out, so this first formula I'm going to use the constant value rule, which says that I'm just going to take n times that constant. So this will be 3 times m, and then this one I've got the 6 over n times, and now I'm going to just bust out this entire formula right here. So n times n plus 1 over 2. So the 6 over n is just hanging out, and then I've got the n times m, oops, as I totally write down the wrong thing, n times n plus 1 over 2. Okay. And so now we are almost where we need to be. So now we've really just got to sort out all this algebra as much as we possibly can. So once again, you just kind of start working this out. So I would start inside the parentheses here and then kind of make my way out to this 3 over n. So I am now going to have, so let's see. As I look through this, these n's cancel out. This 2 will cancel with this 6 to become a 3. So actually this works out pretty nicely. This just becomes 3 times n plus 1. Okie dokie. And so now I'm going to have 3 over n times 3n plus 3n plus 3. So then I get 3 over n and then 6n plus 3. Okay, make some space again. And now we're almost there, so I can distribute my 3n inside. So this becomes 18n over n plus 9 over n. So the n's cancel out. So finally I have a nice simplified answer. So here is the result of just the sum part of that Riemann sum. But remember, the idea behind this was that we wanted to actually take this limit as it goes to infinity. So if I take the limit as n goes to infinity of this, so the question is, what does this represent? So just really quickly, so remember, here was the graph, really, like, so here's just the idea behind the graph, right? So I went from 1 to 4, we just saw that. So the idea behind having this n going to infinity, so this general formula is just for, like, if you had, say, if I had like 4 subintervals, I could just plug in the number 4 and I would actually get the result of the 4 subintervals. I think I have 1, 2, 3, 4. Or if I were to subdivide this into like 8, so you know how usually you have to go through and physically calculate the area? Well, instead of doing that, instead what you can do is you can just tell this formula how many squares you have, and then you will just right away get the answer. But the idea behind a Riemann sum is that the best estimate is the one where you have the most amount of rectangles, because any other way that you do it, you kind of get an overestimate or an underestimate. So the idea is, could we basically get an infinite number of rectangles? And that's why we take this limit here. So then the limit of any constant will just be the constant itself. And then as n goes to infinity here, this part here is just going to go to 0. And so this will ultimately equal 18. And hey, wasn't that what we found before? 18 units squared, 18 units squared. All right, so all of this is panning out. Okay, so now let's use the fundamental theorem of calculus. So whenever you actually use the evaluation theorem, this is what this last part is called. This is called the evaluation theorem. You are using the fundamental theorem of calculus behind this, okay? So this, if I calculate my antiderivative, this would be x squared plus x, and then I go from 1 to 4. Now I can plug that in. So I have 4 squared plus 4 minus 1 squared plus 1. So I get 16 plus 4 minus 2. So this will ultimately equal 18. So the value of this integral will be 18, and it depends on how you're looking at this. So if you're actually thinking about this in terms of area, it would be 18 units squared. If you're just talking about the integral, then it might just be 18. But hey, that is exactly, oops, and sorry, this is unit squared, and then there you go. So now we've got the same number. Oops, same number. Okay, so that is kind of one idea, right? So all of those numbers should match, and it kind of depends on what you're being asked to do, but you have ways to check these things. Now, I promised at the end of the video I would just discuss really briefly when can you use this. So just as kind of an FYI, so the Riemann sums you can always use. So this is always. Also, your definite integrals, so using your evaluation formula, maybe I'll call that we'll call this the eval formula. So you can always use this too. But area formulas, that is a maybe. So 2 out of 3 of these techniques you can always use. The Riemann sums, of course, we know those get pretty nasty, but you can use that. The area formulas depends on what the graph actually looks like. So if you think about these 3, so if you think about just like a parabola, so the graph of this would be a parabola. This is not a circle, so it's not like growing at some nice constant circular rate. So you could not use an area formula here. So no area formula. Same thing with x cubed. So if I think about just what the graph of that looks like, so here's what that would look like, something like that. Same idea, right? So you could not use the no area formula. Maybe I'll just mark that as a formula. These don't have nice area formulas that go with them. But this last one, so this is a constant function. So here's like, pretend that that's 7. So if I'm going from 1 to 3, that would just be a rectangle. So this would be okay to use an area formula. So it just depends on what the problem is when you can use an area formula. Sometimes you can, sometimes you can't. And so that covers the 3 different ways that you can do this, and hopefully that kind of clears up some of the confusion around that. If you have any other questions, feel free to drop them in the comments, and hopefully I'll see you guys next time.